Babies, how we doing? Big things from you guys today. Big things popping, little things stopping is what it's all about. So what we're going to talk about today is put the final piece of the puzzle into circuits, and that's a property called resistance. So we've talked about the idea of voltage as the energy supplier for a circuit, as current. Once we have that closed conducting path, that current is just simply the flow of charge, and that obviously we looked at more batteries providing more energy are going to produce more current. But there is another part of a circuit that is very important that's also used to control the current. So we'll look at the relationship between all three, and that's called resistance. Resistance, as its name, I think just makes the most sense. Resistance means to resist things. So resistance within a circuit is a measure of how much a device is going to control the current that's flowing through it. So for example, if you were to place an object within a circuit that has a high amount of resistance, then that current is going to be controlled a lot more. It's not going to flow as fast. Resistance, think of it literally as we are resisting the flow of charge. If I place something in the path of a circuit that has a very low resistance, then we're going to produce a faster flowing current. So current is going to be affected by not only the voltage source in providing the energy, but you have this idea of resistance. Okay, so resistance, think of it exactly as it is. It's controlling the flow of charge by putting things essentially in its way. Now, what sort of things provide, what sort of things give resistance within a circuit? So resistance is actually found in every component within a circuit. So batteries, for example, have a resistance. Wires have resistance. Bulbs have resistance. And heck, there are devices called resistors whose sole purpose are to actually provide resistance. So I don't know if you guys have recognized that in the simulation you were using, but there are these little tiny resistors that we'll start to fool around with now to try and analyze what's going on with resistance. Otherwise, our main source of resistance that we have been looking at so far are light bulbs, okay? So resistance is found in everything because everything is going to have somewhat, think of resistance as like friction. Everything is going to have some sort of friction because charge cannot flow 100% free through something. There's always going to be a little bit of friction that those electrons are going to experience as they're flowing through a circuit. Now, how do we measure resistance? To measure resistance, we're going to use what's called the ohm. Okay, so this is the one fancy symbol that you saw. This is the Greek letter omega. Okay, like the Omega Burgers, those Greek restaurants that make delicious freaking food, especially breakfast, folks. The spinach and feta omelet. Oh my God, with Euro meat? Get out of here, folks. But anyways, we're going to measure resistance in a unit called the ohm. Okay, so this symbol right here is known as an ohm. So an ohm is going to be a comparison to the amount of voltage that we have, as well as the amount of current that's flowing through that certain device. Okay, so we can think about for a light bulb, how much voltage is it taking away, how much energy is it taking away from the charge, as well as how much actual current is flowing through. And we'll look at that relationship in a little bit more detail. All right, now the thing is we got to talk about what provides resistance. So as I said before, that everything within a circuit is going to provide some sort of resistance. Okay. Key thing is that we talked about in order to have a working circuit, we need the components like the batteries, the wires, the bulbs. We need those things. But one of the main details in order to get charge to flow is we need that closed conducting path, okay, that CCP that I've been talking about. Key thing that we focused on is that within that closed conducting path, everything needs to be made of some sort of conductor. That if we had any sort of insulator in there, that the charge would not flow. And the reason why is that because insulators actually have a very large resistance. So there's two terms that really we're going to focus on here, what's called conductivity. So conductivity is how well an object allows the flow of charge. So think of a conductor has a very high conductivity versus an insulator has a very low conductivity. So the inverse of that, how that relates to resistance, is the opposite of that is called resistivity. If a conductivity is how well it conducts or allows the flow of charge, resistivity is how much it resists the flow of charge. So this chart over here is just a view of how the different materials resist the flow of charge. So down towards the bottom we have rubber and glass. And as you guys should know, rubber, glass, and those things are insulators. Okay, and as we know, insulators do not allow the flow of charge. So look at the values we have here. We have orders of 10 around 10 to the 13th 10 to the 10th. So those are very, 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 very large numbers, which means that they have a very, 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 very high resistivity, which means charge is not going to be able to flow at all through those materials. But if you look at the top of the list where we have conductors, you're going to see their resistivity is very small. 10 to the negative 8th as a magnitude is a very small number. And notice those are like silver and copper. These are the types of things that we use in circuits, especially copper, okay, because they have a low resistivity. They're also very easily accessible for us. They might be cheap, maybe not silver and gold, okay, but aluminum, for example, is. For things that we use within a circuit because of their resistance. Now, the other thing within a circuit is that the path is mainly dealt with. We have batteries and bulbs, but we also have to talk about the wire, okay? There has been something that I've kind of neglected up to this point, but usually we use the wires to connect everything, that the wires really represent the path that charge needs to take. So if we talk about that closed conducting path, the path is really the wires that we're flowing through. So first of all, within the wires themselves, there's a couple things that they depend on. First thing that depends on, as we talked about, is the material. As we just talked about with that resistivity and conductivity part of it, we're going to use materials that have a very high conductivity and a very low resistivity. So things like silver, gold, copper, aluminum. We are not going to use wires made of rubber or plastic. Now note that we do wrap our wires in rubber and plastic because we do not want charge flowing from the circuit to the outside world. We want to keep it contained within that circuit. So material is going to make a difference. Other two variables that do affect resistance is the length and the area, okay? So the length would be obviously the longer the wire. And the relationship here is that the longer the wire is, the larger the resistance is going to be. Okay, so it's a direct relationship here. So the larger the length, that's going to create more resistance. Now, why is that so? It's because the charge is going to have to flow a further distance for a longer wire, meaning that it's going to encounter more friction throughout, and therefore its resistance is going to get larger. Now, the last thing is the area. Okay, the area is to think about it as the thickness of the wire. You're going to see this maybe possibly known as the cross-sectional area. So for a wire, it's just simply a circle, okay? So in this case, for area, the thicker the wire is, the less resistance it's going to have. Okay, so if I were to increase the area, that is going to create lower resistance. That's what's called an inverse relationship. Okay, so these are the three things within a wire, within the path itself, that's going to create resistance. Now, what I had you guys do in the activities and labs you had to do in class was, instead of using wires and all the other things as resistance, I had you guys, without even knowing, the simulation by itself has the wire resistivity, even the battery resistance. All their resistance is turned down very low to essentially they're nothing. Okay. So the things that we were using as resistors were the light bulbs. So we had the light bulb here, and in this one we had two light bulbs. So our main source of the resistance were the light bulbs. And you'll notice that each light bulb, as a general thing in that simulation, each light bulb had a resistance of 10 ohms, okay? So the one thing I did have you guys focus on was the relationship between resistance and current. And I think this is a pretty simple idea. Understanding the resistance as a word means to resist, to try and stop something from doing something. Okay, so as we looked at here, notice that in this first diagram I have a single bulb that has a resistance of 10 ohms. So notice that with one bulb, I'll just write 1B, notice that we have a current of 1.80 amps. Now in the second diagram, when I have two bulbs, notice it's now creating a current of 0.90 amps. So the one thing I want you guys to recognize here is what's the relationship between resistance and current, is that if I increase the resistance, and by doing this I'm increasing the number of bulbs that I have in my circuit, what that's going to do is it's going to decrease the current within that circuit. So that's an inverse relationship overall. Okay? So why we use resistance within a circuit is to control the flow of charge. If I want a lot of current, I'm not going to want a lot of resistance. If I want very little current, I'm going to use more resistance in that way. So resistance is a way for us to control the flow of charge, to control where the current goes and what it does. All right, now putting this all together, obviously we looked at the relationship so far between voltage and current, between current and resistance. So now let's tie all these things together. So what's the relationship between voltage, current, and resistance? And this is one thing I tried getting you guys to see if you could figure out in that little lab simulation. So just to kind of look at these two examples, here I have two batteries in series. So if we know two batteries in series, their voltage should be a total of 18 volts. Okay? We have our resistance here of 10 ohms and our current of 1.8 amps. Okay, so the current, what we talked about is that current is related first to the batteries. Batteries provide the energy. So here we have 18 volts of energy. We have 10 ohms of resistance. And in the end, what I get overall is 1.8 amps of current. So mathematically, there is actually a relationship. How do I get from 18, how do I take 18 and 10, I should say, and get to 1.8 amps? Understand that what I would do is divide these two things out. If I take the voltage and divide it by the resistance, that's going to tell me the current within my circuit. Notice the same relationship here. If I have 18 volts again, and I have now two bulbs, so that would be 20 total ohms, and I get a current of 0.9 amps. Think about this again. If I were to divide 18 by 20, that's going to give me 0.9 amps. Okay, doubled the resistance. Notice the current got cut in half. So again, voltage divided by resistance gives me the current. So putting together, this is known as Ohm's Law. Okay, Ohm's Law describes the relationship between these three variables. We have the three main important variables: voltage first, which is the energy source. You have resistance, which we use to control charge, and then you get current, which is the actual flow of charge. And again, the whole purpose of the circuit is we want charge to move so that we can utilize the energy that it has. So what Ohm's Law states is that the current in a circuit, so this describes how and what amount of current is going to be produced. It says is directly related to the voltage, so directly related, and is inversely related to the resistance. Okay, directly related means that whatever I do to the voltage, I'm going to have the same effect on the current. An inverse relationship for resistance means whatever I do to resistance, it's going to have the opposite effect on the current. We'll talk about that in a little bit. But as a relationship, you get the equation I equals V divided by R. Okay, if you want to write this out differently, whoopsies, it would be I equals V over R. Sometimes you'll see this written as V equals I times R, ver, if you will. Many different ways that I can organize that equation, but this Ohm's Law describes, again, what is happening, what kind and what amount of current is actually produced within a circuit based upon the voltage, which again is the energy being supplied, and the resistance, which is how much, well, resistance that current is going to face. All right, so now kind of putting this all together, here's some quick examples. So again, if I want to find the current produced, notice that I'm not giving you that ammeter in here. So if I just want to find this current, here I have, again, two batteries in series, so that would be 18 volts total. I have two light bulbs together, which would be a combined 20 ohms of resistance. So if I take 18 volts and divide it by 20 ohms, that would give me a current of 0.9 amps. Okay, so again, we're using Ohm's Law here, which says that the current produced is the voltage divided by the resistance. All right, next one, I have three batteries placed in series. So three batteries in series would give me 27 volts. I have one single bulb, so that would be 10 ohms. So if I divide those two out, I would get 2.7 amps. Okay, so notice the difference here. I had less batteries. Less batteries are not going to produce as much energy for the charge to flow, and then more resistance. So here I had more voltage and less resistance, and notice the difference in the current. This would be 3 times as much current that we have there. All right, last one, just a couple extra sass here. Okay, I've got 4 batteries here, but notice that I have 2 and 2 in parallel. So that would be a total of, if you remember, 18 volts. Okay, in parallel, we just look at the 2 that are in series. I then have 3 bulbs that are placed together. So if it's 3 bulbs, think of what the resistance would be, which in this case would be 30 ohms. So if I take 18 volts and divide it by 30 ohms, I would get 0.6 amps of total current. Okay, so this is using Ohm's law, looking at the relationship between voltage and resistance to find the current that is produced. Okay, so again, variable-wise, current, which is the flow of charges of what we're trying to produce in a circuit, is related to two things now. It's kind of summarizing everything. It's related to the voltage and the resistance. Voltage is energy. So the more voltage you have, the more energy, the more current you're going to get. But at the same time, we have resistance. Resistance is created by all the components within the circuit, batteries included. Okay, even the wires, bulbs, whatever it might be. Resistance is trying to control the flow of charge. So the more resistance we have, the less current you're going to have. So the two relationships is what's called a direct relationship, okay, and an inverse relationship. So let's just say that I had, in this case, 120 milliamps, milliamps of current, okay? What would happen to this current if I were to double the voltage and I were to triple the resistance? What would that do? So understanding the variables, here's what I know. Okay, is that if I have 120, God bless America, 120 milliamps, so just write it as MA. Okay, if I were to double the voltage, doubling the voltage is going to have a direct effect on the current, which means whatever I do to voltage, same thing is going to happen to the current. So if I double voltage, I'm going to take my current and double it. So what that would give me is 240 milliamps. More energy means more current. But now let's say I were to triple the resistance. Well, tripling the resistance means I'm making the resistance bigger, which if the resistance gets bigger, that's going to minimize the flow of charge or the current. So current is actually going to decrease. So what I'm going to do here is that if the resistance is tripled, what I'm going to do is take my current and divide it by 3. I'm going to do the opposite. The opposite of tripling. Tripling means times 3. The opposite of that is dividing by 3. Okay, so again, think of inverse as opposite. So if I take 240 milliamps and divide that by 3, I should get 80 milliamps. And that would be my final answer. Lock it in. All right, so babies, so this, again, tying everything together, introduce the last concept of resistance, but then also want to introduce that Ohm's law, which ties together voltage, current, and resistance. All right, now that we understand kind of the fundamental properties within a circuit, what we're going to venture on to now is actually get into a little bit more complicated circuits. So what are the different things I can do, the different ways I can arrange components within a circuit, okay? And we're going to talk about what happens to voltage, current, and resistance when I do that. If you've got any questions, make sure you jot those things down. See you guys later. Peace out.